Okay, so let's continue our workshop. And it's my pleasure to introduce the next speaker, Gregor Kemper, from the Technical University of Munich, with his talk, Distant Geometry, Algebra, and Drones. So please, Gregor.
Yes, thank you very much, Artem. I'm happy to give a talk here. So this will be a little bit of invariant theory and some combinatorics and lots of applications. Let's see, and it's all about joint work with Mireille Boutin, and some of it is quite old, and other parts of the talk, the second part of the talk, in fact, will be quite recent and up to ongoing work. Okay, let's get started. So the first part is the old one, distance geometry, some question about that. It's almost 20 years old. No, it's more than 20 years old. So we started with a question of computer vision. If you give yourself some point configurations, have the computer decide which of these are equal. So one obvious idea of doing that is to use the distribution of distances, which is given here as a histogram. So for these two constellations, you can see that the histogram of distances is in fact different. And that raises the question whether this distance is actually an invariant that always distinguishes between point configurations. And here is the question posed by Mimi Boutin, as I said, more than 20 years ago in a more mathematical way. So is a point configuration uniquely determined up to the action of the relevant group, and this is the Euclidean group times the symmetric group acting on the points, is it determined by its distribution of distances? So does the distribution of distances separate all the orbits? That would be very nice, and it would probably be too good to be true. Because, in fact, when we thought about this question for a while, we found a counterexample, and it's given by these two 4-point configurations, so quadrangles, both of them. And the second one is just obtained by mirroring down the upper point here downwards, and then it ends up here. And right, the configuration, this quadrangle, is fine-tuned in such a way that it just so happens that this distance 2, which appears here, makes a new appearance down here. So that means that the distribution of distances of both these configurations are the same, but they are quite visibly not the same. They are not in the same group orbit. So here we are. There is a counterexample, and so the general answer to the question is no. And yeah, probably come to think of it, the question was really too naive or too optimistic, because when we consider the distribution of distances, that is really an invariant under the group S n choose 2, acting just by permuting all the mutual distances. There are n choose 2 of them. So in a sense, we were using the wrong group when we even asked that question and entertained that hope that the distribution of distances would in fact distinguish all the orbits. However, when you look again at this counterexample and realize that I said, yeah, it's fine-tuned in such a way that this distance 2 reappears down here, it may give us some hope that in fact we may have something there. And in fact, what helps us out here is that the distances, the entries to mutual distances in general, are not general, but they satisfy some algebraic relations. And here they are. So we might formulate the relations that are satisfied by the square distances between the points, now n points in m-dimensional space, the relations that are satisfied by them by minors of the so-called Cayley-Menger matrix. And when you write down or classify the relations, that means you're giving a second fundamental theorem. So this would be the second fundamental theorem of the Euclidean group. The squared distances are generating invariance, and these are the relations given by the, as it happens, m plus 3 times m plus 3 minors of this matrix. Now, how does this arise? This actually arises from the Gram matrix of the scalar products between the connecting vectors of the points. You choose one anchor point, and then you have the connecting vectors, and then that gives you a Gram matrix. And this is really nothing else than blowing up the Gram matrix a little bit and performing some operations on it. Then you get this Cayley-Menger matrix, which is nice because it doesn't need to specify or to select any anchor point to give it. So it's a nice matrix, and it turns out to that its minors represent all the relations. So to give just an example to get your hands on what is n and what is m, for example, when you consider 4 points in the plane, then you get precisely one relation here. So in other words, within the set of all graphs, weighted graphs with six edges, within that set, the distance graphs form a hypersurface. They form a hypersurface. Okay, that's given by just one determinant vanishing, the Cayley-Menger determinant vanishing. Okay, so as it turns out, and this is the main part of the work we then did, that in this case and in other cases as well, those permutations in the S6, the symmetric group in six letters, that map this hypersurface into itself are precisely those that come from S4 in the sense of they are a permutation of the edges that really come from a vertex permutations. So they are S4 are the vertex permutation. Every vertex permutation induces a permutation of the edges. And those permutations in S6 that map the hypersurface H into itself are precisely those that come from S4. And that helps us a great deal, because if we have two point configurations that share the same distribution of distances, that means that there exists an element from the S6 that maps the edges one to each other. But since both sets of edges come from an actual 4-point configuration, that means that both lie in H, and that means that for most point configurations, it is in fact true that the only permutations that map the edges, the mutual distances onto each other, they come from S4, so they are the good ones. And this means that we have achieved the following theorem. So let me sort of read it out to you. It says that almost all point configurations are in fact reconstructible from their distribution of distances. So there are counterexamples, but they need to be finely tuned. And the more precise statement, well, it needs that the dimension, that the number of points n is bigger than or equal to the dimension plus 2. And then relations of the Cayley-Menger type start to kick in. And then we proved by a combinatorial argument on, leading monomials of relations and so on and so forth, that then we have in fact, the reconstructible point configurations form an Zariski open dense subset among all point configurations. Okay, so that's the theorem that we achieved here from this. Yeah, and this has some potential applications. In the meantime, it got quoted quite a bit. Incredible though it seemed at the time, we still, or we believe ever more that we are really the first ones who prove this result. Okay, so this actually brings already the first part of the talk to its conclusion. So are there any questions in the meantime? Yes? No question. All right. So we go on. Now let's go to the second part. That's the more modern part. Can a drone hear the shape of the room? That sounds very applied. Anyway, here again we have a starting point, and the starting point was a theorem by 5 authors whose names I won't dare to read out because I'll make mistakes. What it says is you consider a room with a loudspeaker and at least 4 microphones placed in the room at random positions. And then they say that with probability 1, the first order echoes, that is no bouncing echoes around in the room, but just one bounce, the first order echo of a sound from a loudspeaker and just one sound of the loudspeaker uniquely specify the room. So you can reconstruct the entire room from just hearing the echoes from one single sound event. So we found that very intriguing result that you can do this. But we didn't quite manage to understand the proof that the authors gave in the paper. And well, so given that we've found this an intriguing, fascinating result, we try to make our own sense of it all. And in the second part of the talk, I'd just like to take you along with making sense out of this. So let's get started. What do we have? We have a room with at least 4 microphones and a loudspeaker placed in it. So here's the room and loudspeaker and microphones, as you can see. Now this has lots of symmetry, which is sort of unintended, but it's for ease of drawing. I drew the room with these symmetries. So there's a sound event. So the loudspeaker sends out some sound, probably a high-pitched and short duration sound, so that ray optics can be used. Okay, so the sound bounces off the walls and then gets received by the microphones. And what they do, we assume that they know when the sound was sent, so they measure when they hear it. So in effect, they measure the distance traveled by the sound. That's what the microphones can do. All right. Now, what happens, of course, is not just the loudspeaker is omnidirectional, so it sends out its sound and it gets reflected at all the walls, not only one. So there's a lot going on in that room, and all the echoes get received by the loudspeakers, by the microphones. Now, the problem, of course, is sound has no color, right? So the microphones just receive a slew of echoes, but they don't know which is which. And in particular, they need to identify which of those echoes are, say, the green ones. In other words, which of those echoes come from the same wall and which come from other walls. If they can do that, then the rest will be just sort of elementary geometry. But it's this matching problem that is the hard one, because we may also assume that the echoes all sound roughly the same. So there's no way to identify them physically, acoustically. You have to do something else in order to do this, what we call the echo matching. Okay, so let's analyze the situation further. And in order to do so, let's, for ease of drawing, go to 2 dimensions. Well, the drawing was always in 2 dimensions, but now let's be honest, this is 2-dimensional. And then be consistent and say, in that case, we only have 3 microphones, because 3 microphones in 2D give the same information or equivalent as 3 microphones as 4 microphones in 3D. So, okay, we now restrict ourselves to one wall. So we have bouncing business, but this can be modeled by a mirror point. So this bouncing of the sound rays is the same as if the sound was just from the onset sent from an echo point S, which arises from mirroring the loudspeaker at this wall here. Okay, so that's the so-called mirror point. It's a virtual sound source. And then, having done that, we might as well forget about the wall altogether. All that matters is the point S, and also all that needs to be identified is this point S. Because if we do know where the microphone was and we know S, then the wall will be just what's right in between the points of the same distance from S as to the loudspeaker. So we need to identify S. And what we are measuring is also these three distances, because as I said, the loudspeakers know, the microphones know when the sound was sent, and they even better know when they received it, so they know the total distance traveled by the sound, so they know D1 up to D3. They also know the distance they have between each other. And that gives us our déjà vu element. Because now, when we fill in these three distances that are also known, that we can assume to be known, then what we have is a 4-point configuration. And so we are back to where we were 20 years ago. We obtain a relation, right, between these distances. And just to give you a rough idea how this looks, this is the relation you would get with the values I inserted here. You get this relation between the D1, D2, and D3, the little d's, right? The big d's are the distances between the microphones. All right. So you get these distances, and so that means that when the sound actually does come from the same wall, which means it comes from the same mirror point S here, then the measured running distance, distance traveled by the sound, the three distances satisfy some relation. And this is very nice. So let's summarize this result in a proposition. So now let's go back to the three-dimensional situation that we are really interested in. So again, we have 4 microphones, M1 through M4. We should assume them to be non-coplanar. They don't lie on a common plane, otherwise they don't have distinguishing power enough. And then we are given the D1 up to D4. And these are, for the proposition, just non-negative real numbers. And as it turns out, they may come from a common source. That is to say, there exists a point such as the mirror point, such that the DI are realizable as the distances of the same point to the microphones, if and only if the Cayley-Menger relation holds. Okay? And this is quite interesting. What I've explained to you is that one direction, right? If the distances all come from one and the same mirror point S, then the distances satisfy this Cayley-Menger relation. But in fact, the converse also holds. So if this Cayley-Menger relation is satisfied, then there exists such a point which realizes the given D1 through D4 as distances from this point. So it's realizable in that sense. In other words, when you're given the distances D1 through D4, to determine whether these distances actually come from the same mirror point, equivalently they are echoes from the same wall, using this Cayley-Menger relation is the best you can do. It's the best you can do unless you have some other tricks to determine, the echo from this wall sounds different from that one, but you usually don't have that, right? So if you just have the distances, this is the best you can do. Okay, so this clearly means that we now have an algorithm just use this relation to try to figure out, to try to perform the echo matching. So here it is. We call it the wall detection algorithm. So sort of pre-processing step number one, first just collect the travel times and therefore the distances traveled by the sound. And this is for each microphone separately. You have you have sort of lists of echoes that you received. And now step two is the echo matching. So you just try all four tuples, D1 through D4, combinations of echoes that you received. And for each of them, you test the Cayley-Menger relation. And if it holds, then you just assume that these distances, these received echoes, actually come from the same wall. And then you do as if it were like this, and then the rest of the algorithm is, as I said, elementary geometry. You can, from these distances, then under the assumption that they come from the same point as you can compute this point, and then since you also know where the loudspeaker is or was, you can, from that point, compute the wall, which is what people really wanted to do. Okay, so this is how you can do the echo matching. Right. So let's go on. Well, because this relation is guaranteed to hold for all echoes coming from the same wall, that means that the algorithm has to be detected, is guaranteed to detect every wall, well, from which at least a first order echo can be heard, right? Every wall where the microphones are situated in such a way that they do hear the echo from this wall, such a wall can be detected. So that's on the plus side. There's also a downside. It may, of course, happen that this Cayley-Menger relation is satisfied purely by coincidence because walls are just arranged in such a way that even though the echoes come from several different walls, by coincidence, they do satisfy this relation. And this becomes even more interesting if you're working in the real world, where it's not enough to just determine whether something is zero, but you have to determine, is it close enough to zero, taking into account measurement errors that you will consider it equal to zero, right? Then this becomes even more, so to speak, less of a coincidence that this relation will seem to be satisfied, even though it's by pure bad luck, right? So this is what we and others also call ghost walls. If walls are detected by this echo matching and then wall computation algorithm that are not actually there, that just exists by coincidence. Okay, so how does such a coincidence, what does such a coincidence look like, or what may it look like? Well, here's one example. So I drew, again, this is in 2D for ease of drawing. I drew three walls here, W1 through W3, and these are the trajectories of sound. So you can see it, and now here's the ghost wall, which will in that case be detected. So here's a situation where the microphones receive three echoes. In reality, they come from three different walls, but the timings when they arrive will be exactly the same as if they were reflected by this ghost wall down here, which does not really exist. That's why it's painted in red. So that's an example of a ghost wall. And yeah, actually, this is an example that we didn't think up, but that came out of the computer calculations that I will come to in a few moments. So we didn't think this up. This actually, the computer gave this back at us, and then we just made the drawing. And so, yeah, it's actually the counter. It's an example of a ghost wall. Right. So in unlucky circumstances, this can happen. And when you look at this for a little while, you see that the vertical distance between wall W1 and W2 is the same as the vertical distance between these microphones and so on. So that's really the reason why this why the travel distances here match each other precisely. Okay, so ghost walls may exist. And that of course raises the question, can they be avoided? Or do they arise often? So very much in the spirit of reconstructibility, where also we achieved a result that most point configurations are reconstructible. Here it is also, can the microphones at least be positioned in such a way that no ghost walls are detected? And this is also what the former paper I told you about says, that with probability 1, they say all the walls can be correctly detected. Well, and as it turns out, and I'll later on explain a little bit more about the details, this question can be translated into a question about polynomial ideals. So there you get into computational commutative algebra. And by using, in this case, very easy Gröbner basis calculations, the results quoted above can be verified. We verified it, and this way we gained our own understanding. And this would be the theorem in another formulation. So consider a given arrangement of walls, and that includes ceilings, floors, sloping walls, anything you might have, plus a loudspeaker. And then, given this, you can now position the microphones in the room in an arbitrary way. And because there are 4 microphones, this gives a 12-dimensional configuration space. And then within those space, the positions of the microphones where ghost walls are or may be detected, they lie in a subvariety of lower dimension. So the good microphone positions are in a Zariski open and Zariski dense subset, or they include a Zariski open dense subset. Okay, so that's not too bad. Right. So much about gaining our own understanding. Now, having done that, we were thinking maybe we can also in some way improve on their result, and that brings in the idea of a drone. So this would be, the whole thing would be more useful if you didn't have 4 separate microphones on their separate microphone stands and so on and so forth. But if you had a drone that has 4 microphones mounted on its body and fixed positions on the body, you fly it into the room. The room also has a loudspeaker somewhere positioned in it. You fly the drone into the room, and then the drone does precisely the same thing. It collects the echoes from one sound event coming from the loudspeaker, and then does our wall matching algorithm and tries to map out the wall in just one instance, so to speak. So does that work? And the question is, how is that different? Well, it's different because now we don't have 12 independent parameters anymore, but just 6, because the possible drone positions are in a 6-dimensional configuration space. And there are bad positions where ghost walls occur. Now, the thing is, when you say most positions are good, that means you can get out of a bad position, so to speak, by an infinitesimal movement. Now, when you have a 6-dimensional configuration space, that gives you much less freedom to get out of a bad position. So the question is it still true in that case that the bad positions are rare? And that's a harder question because the configuration space is lower dimensional, from 12 down to 6. Well, as it turns out, the answer to that question is also true. It's also correct that with, in Zariski open dense subset of all possible drone positions, which are now governed by the affine special orthogonal group, almost all drone positions are good. That is to say, it's guaranteed that no ghost walls will be detected. So we got that too. And here's a little bit about the proof strategy. So I just repeat the theorem. And then what we do, well, we consider the Cayley-Menger relation, this FD. This ref stands for reflection of the loudspeaker position at the wall W1 up to the wall W4. So these are the positions of the mirror points, right? And M1 through M4 are the microphone positions. Now that this is not zero happens to be a Zariski open condition on the microphone position. And that's very important that this is Zariski open. Now we introduce one concept. We call a drone position very good given the set of walls if this becomes an equality only if the walls W1, W4 you choose here from this set of walls are all equal. So a very good drone position is certainly a good drone position, although the converse does not hold. But very good is good enough for us in the sense that we could prove that, well, there always exists a very good drone position if the microphones are not in a coplanar position, which we assume they are not. Okay, so we can prove that there always exists one, and then because of the Zariski openness, you take the union of finite many Zariski open subsets. It's still Zariski open. Therefore, if it's non-zero, it's dense. Right? If it's non-zero, it's also dense. That's because of the Zariski openness. So what we need to do is to translate this statement that there exists a very good drone position if the MI are not coplanar. We needed to translate that into a statement on polynomial ideals, and that is quite possible. So that is doable. And then the work really starts, because this statement about polynomial ideals then leads to, you know, a polynomial ideal problem in 36 variables. And as I guess we all know, this is very hard to do. And so we needed some strategies, some tricks, and so on to make this verifiable. And in the end, we did with some computation time to verify this. So this is not the computation time that goes into the echo matching algorithm, but it's the computation time that goes into proving the theorem, right? And that was, in the end, it was just a couple of minutes after we massaged it for quite a while. But without massaging, it would probably not have finished within our lifetimes. Okay, so what we are missing still is a purely conceptual proof of the thing. So we needed to put this into a statement of, well, containment. One ideal is contained in the radical ideal of another ideal, and then just try to verify it by magma. We didn't get a conceptual proof of it. Would still like to get it, but have not. So that's, anyway, that's the proof, or the rough strategy of the proof. There is one more question that occurred to us. Let's try a little bit more. Wouldn't it be even better if we didn't, as in the previous picture, if we didn't have to put the loudspeaker, so to speak, on a stand somewhere in the room, but if we fly in the drone into the room, that it brings its own loudspeaker on its body. So what about that? That would be even better. And yes, we proved that too. So in this circumstance where the loudspeaker also sits on the drone, on the body of the drone, the same is true. Now, why is that different? Well, that's different because If the loudspeaker is fixed, then these mirror points, the reflections of L at W1 up to W4, they just become fixed points. They are arbitrary, but they are fixed. Whereas when the microphone is on the drone, then these reflection points, the mirror points, they become moving targets as well, okay? And that makes everything much, much, much harder computationally. Okay, so the computation here is quite a bit harder. Right, but we achieved it, and that's this story. Now, you can say this is all very well, and it's got a nice potential application, and talking about drones is quite fashionable these days. But in fact, it's not really applicable, because if the drone wants to do its measurements, it should probably, at least for a moment, stand still in the room. So it should be a hovering drone. However, a hovering drone only has 4 degrees of freedom. It can't turn like this, because when it turns like this, it will drift away, right? A hovering drone only has 4 degrees of freedom, and asking the same question makes it harder still. Less degrees of freedom means less possibilities to get out of the bad position. And here's again the bad position that we had again. And now I'd like you to consider this situation, and just imagine in 2D, these 3 microphones are mounted on a drone, and now they have the 4 degrees of freedom, which means they can somehow turn horizontally around. They can move up and down, but they can't tilt like this or like that. They can't do that. And that means that the whole arrangement moves up and down, and that means that the ghost wall here never disappears. It will move with the drone, it will move up and down, but it will not disappear. So in other words, at least by an infinitesimal movement, with the 4 degrees of freedom that we now give the drone, it will never get out of this bad position. And that means we have a fundamental difference here when we restrict the degrees of freedom even further. Okay, so in this situation, you can't easily get out of a bad position, which also means that the good positions are not contained in a Zariski open dense subset. Now, we gave this a name. The drone is deceived by its own image. Whatever, that's because the distance here between the walls are the same as the distance between the microphones. So somehow we gave it that name. And then what we proved is that this situation, deception by its own image, in fact, precisely characterizes those cases where not almost all positions are good. So it's just this situation where you have this phenomenon of deception by its own image. They are precisely the situations where the good positions do not contain a Zariski open closed subset. Okay, and the proof is still harder, as is to be expected. It's a bit counterintuitive, because you have less degrees of freedom, but still the proof is harder. And we could only do this for a fixed loudspeaker in the room, for a loudspeaker carried on our vehicle, which may also be ground-based in this case. It's the same result. The loudspeaker carried on the vehicle, we just couldn't get the computation through. We ran into an impasse computationally. Right. And maybe the fact that things behave different in this situation also might give us a hint that maybe it's not our inability that hindered us from giving conceptual proofs. Maybe these things are just in and of themselves unsystematic. So, you restrict the situation a bit, you get a really different result like this one. Maybe there is no conceptual thing behind this. Maybe you do have to make these computations. Anyway, I'm getting to the end of my time and also to the end of the talk. So further directions. This is the ongoing part. I already said one or two words about how to deal with inaccurate measurements. When it comes to real applications, to real life applications, this is of course the elephant of the room. How do you deal with that? And well, we have some ideas which seem to be working, but we are not even far enough to have written them up. So we still need to do some more research, and then we hope that something will come out of it, but we are quite confident that we can say something useful about this as well. Another direction would be imagine the drone or whatever microphones you have do not know the time of sound emission. Interestingly, then the problem, even the problem of reconstructing the point when you have done the matching, comes down to the same mathematical problem that is the GPS problem. And we have worked on that. And in fact, we just published on the archive an article about the GPS problem and the uniqueness of it in October. So we were quite surprised to find that the experts in the field still didn't understand the uniqueness of the GPS problem very well. And so we think we contributed something to that. Came as a surprise to us that there even was something that could be contributed. A further question would be, well, can we also, not as before, assume that the drone knows exactly where it is, but turn things around and use echoes to self-locate the drone or whatever other vehicle we have. And as it turns out, you can actually do the SLAM problem, that is simultaneous self-location and mapping out of the room. So now we also have an algorithm for that, but again, that is still in the process of writing up. Okay, so that's all I wanted to say. Thank you very much for your attention.
Thanks a lot for your talk. Okay, are there any questions or comments? Okay. Yes, John, you can speak.
Yes, thank you, Gregor. So all of your results assumed that the microphones were not coplanar, and just imagining my picture of a drone, and it has sort of 4 spinny things either side, and they're the obvious places to put the microphones. So it seems like it might be useful to work on the same problem under the assumption that microphones are coplanar. Is that impossible, or?
Well, yes and no. So, first of all, of course, you're right. In fact, the way I drew the microphones on the drone, you know, I put a trap for myself, right? Because they were sort of the drawing suggested that they are coplanar. The thing is that even when you've done the echo matching, imagine you have all the microphones on one plane, and here's the actual echo point. So I don't know if you can see my hand movements here. So here's the echo point. Then the distances to all the points on that plane, including the microphones, are the same as if the microphone had been on the exact opposite side of the plane, which means that when the microphones are coplanar, you can never distinguish this point from its mirror image mirrored by the plane. And that's why it's a very bad idea to have them coplanar. And in fact, you can say more. In fact, you can say that 3 microphones give you the same information as 4 microphones when they are coplanar. They can do the same thing. You measure these 3 distances, it's the same thing. They specify the point up to 2 solutions, right? Mm-hmm. And therefore, no, you'd better put them in the drone in such a way that they are not on the same plane, which I do believe drone builders would say it's not a fundamental problem.
Yes, thank you.
Okay, Ben, do you have a question?
Yes, I have a question about, this is about the 20-year-old result, about most point configurations are reconstructible from their pairwise distances, which is, it felt familiar to something I've been thinking about a lot recently, which is just instead of the whole Euclidean group, just the orthogonal group. So now the set in question isn't the pairwise distances, it's all of the pairwise dot products, including the self dots.
Right.
So that's a generating set for the invariant ring.
Mm-hmm.
And the relations are given by the second fundamental theorem. So it's like a similar setup.
Yeah, it's also minors of the Gram matrix.
Exactly.
Mm-hmm.
So are we going to get the same thing where the
no
variety
idea.
is fixed by only the, so I can act on the set of pairwise dot products, say separately on the diagonal dot products and the off diagonal dot products with two different symmetric groups. Is it again going to be the case that the only ones that fix the variety defined by those relations are the ones that are induced by the symmetric group acting on the indices?
It's an excellent question, and I don't have the answer. My answer is it's a whole new game.
So it's not clear that the
No,
technique that you
not
guys...
at all, not at all. Because see, if you have the you have if relative from our point of view, you have an anchor point which you fix, right, which will be the origin of your space, and then you have the distances, the connecting vectors between this point and all the others. So it's a whole new business. The variables will be different to start with, and then in our argument we used actually monomials occurring in those relations, but monomials in terms of the distances, right? And so when you have those scalar products, it's a whole new game. So I can't make any prediction whatsoever about what this new game. You'd have to start from scratch, basically. But yeah, when you ask me for a gut feeling, my gut feeling would be it might just work. It might just work. Because we've done similar considerations in like in the projective case and in the case where you, instead of mutual distances, you take areas of triangle and stuff like that. And whenever you do this, you get into a new game, and the game's always worked. So your game might also very well work.
I got you. Thank you
but
so
it's
much.
a new game. It's a completely new game. I think it's a great idea.
Got it. Awesome. Thank you.
Okay, thank you for your questions. Are there any other questions or comments? Okay, then I have a question. And what about if we have two speakers? Not one, but two speakers, and we can distinguish the sound. Does it go from the first or from the second one? Have you thought about what will happen in this case?
Not specifically. So they do their sound event, and it's basically, it comes down to working with one speaker, but do it twice, right? Or shifting the one speaker to another position and doing it again. So yeah, of course you gain more information, and there's a great likelihood that if you're in a bad position with respect to the first speaker, you will not be also in a bad position with respect to the second speaker, which is at a second position. So it will greatly enhance chances of not being in a bad position, and it will also enhance your possibilities when it comes to inaccurate measurements, to noise, right? However, we haven't specifically studied the problem. We found the one where you just have one loudspeaker and just one event particularly attractive, because it's so charming, right? You just have one sound event, and simultaneously you can reconstruct the entire room for just one event. If you have 2, so much for the better. So no, we haven't specifically studied it, but I'm not sure that it will really bring in much in the way of a qualitative advance, rather than just having the quantitative advance of having just two of the same. Does that make sense?
Yes, okay, thank you. Are any further questions or comments? Well, it's not the case, so then let's thank the speaker again.
Thank you very much. So I stop the presentation.
Okay, thank you a lot. So